Hi everyone, this is Dr. Anirban Sengupta. I'm an associate professor in CSE at Indian Institute of Technology, Indore. So today I would like to talk about robust digital signature method for securing IP cores against fraud, ownership and cloning. Uh, this work has been published recently in IEEE Transactions on Consumer Electronics, and it has also been presented in IEEE ICC Berlin 2019 at Germany. So let me give you an outline of the talk today. So I would like to start talking a bit about the introduction, followed by the existing approaches, then giving a glimpse of the flow of the proposed approach, extending with the motivational example, and finally summarizing with the experimental conclusions and inferences. So what is a DSP and multimedia? So as we know, and I had spoken a bit about this in my previous talks as well, digital signal processing cores and multimedia cores are reusable IP cores that are very integral part of the SoC designs, and they are used in abundance in consumer electronic products such as MP3 encoder, JPEG, digital camera, tablets, in image compression, video compression, and several other applications. The global semiconductor supply chain for SoC design is highly vulnerable to security threats such as intellectual property or integrated circuit cloning and false claim of ownership. So in this talk, I would like to discuss and describe about the recent work that my group and I have done, which is called crypto digital signature method for securing against IP and IC cloning as well as false claim of ownership. Some of the existing approaches that exist in this field are the ones which employ watermarking as shown in references 1, 3 and 4, which you can see at the end of the presentation. So these watermarking based methods use mostly two or multivariable author signature scheme for protecting DSP hardware IPs. Now what I mean by the word that they use multivariable author signature is that the signature combination can be formed with multiple variables. So they usually have different encodings present for different variables, and these encodings have a specific decoded meaning based on which the constraints are implanted onto the design. There is a designer's specified encoding rule, as I said, for each of these signature variable. However, one of the most important drawbacks of these approaches are that the security of these approaches in terms of proving or authenticating the rightful owner stays intact as long as the signature and the encoding process are not compromised or leaked. So once these are compromised, the vendor or the actual IP maker owner fails to prove his IP ownership. And it is also possible that due to the leakage of the signature, detection of IP cloning or authentication of the rightful owner during detection of IP cloning and counterfeiting process may not be feasible. So summarizing the novelties of this particular proposed method, which I have come up with, is first it proposes or uses a multi-level encoding method which is driven by encrypted hash based digital signature for protecting or securing a DSP application. Now DSP applications here could be any form of signal processing or multimedia application such as digital filters, which could be Butterworth Chebyshev, or it could be infinite impulse response filters of other types. It could be finite impulse response filter, which is used in audio compression and wireless devices, headsets. It could be a JPEG compression decompression core. It could be a discrete cosine transformation. It could be a fast Fourier transform or discrete Fourier transform, or it could be a hard wavelet transformation. So there are several such applications. We can keep going on and on to speak about the utility of these DSP applications in the consumer electronic products and systems that we see around us everywhere. So we have a novel methodology in this work for encoding the DSP application. So we basically extract some of the information from the DSP design that we use for implanting as a signature later through an encoding algorithm. And finally, the genuine designer or vendor is able to prove his or her ownership over the design by using the digital signature, which provides a more meaningful, scientific, and definitive way of proving the ownership than just right away using a digital signature or a signature from the watermarking process. Okay, so let us get into this approach. So this is a novel crypto digital signature approach which incorporates the following security modules. So we have a crypto hash function which we have like as a SHA-512 block. We have a crypto encryption function which is RSA, and we have two layered encoding algorithm. The generic steps of generating the digital signature includes the following. The first is to generate a bitstream representation of a DSP core. Second is to perform SHA, which is secure hashing on the bitstream generated. Then it performs some sort of post processing followed by RSA encryption, which is the place where we actually encrypt the hash using a private key, and then we follow that with another post processing. So a very important thing to note here is that in case of generating a digital certificate or a digital signature, the modules are actually signed off with a private key and not with the public key as we have generally in case of RSA. So this is a flow of the proposed approach. So at the inputs we have a DFG, which is the data flow graph of the DSP application, which is the intermediate representation of a DSP hardware IP that we can generate by either starting with the analog form of the application, followed by doing some bilinear transformation, and then getting into a mathematical function, and then following it up with a graphical representation of that. Then we have a resource configuration, which is the designer specified resource constraint that must be adhered to and must not be violated. And based on these two inputs, the first pre-processing block starts by constructing a scheduled data flow graph and assigning of storage variables at the inputs and outputs. Then by using an encoding rule, we generate the bit streams. Then we perform SHA, which is secure hashing, by calculating the digest of the input bit stream, followed by doing a post processing which divides the input bitstream digest into m blocks of size n bits each. Here the value of m and n can be chosen by the designer, so we don't have a hard binded rule here for the value of m and n. Then each of these n bit blocks are converted into its respective decimal equivalent. So this completes the post processing block 1. Now once we have that, then we start performing RSA encryption, where we encrypt each decimal value using RSA. And as I said, here the RSA accepts a private key of the IP vendor based on which it generates the digital signature. So in post processing block 2, next we construct the final bit stream from the encrypted decimal values. And once we have the bit stream in a binary form, this is what is technically called a digital signature, which is nothing but signing off the hashed value of the given design. Now once we have that, then the next process now is to use this stream of ones and zeros to encode in the DSP application as a digital signature constraint. So we need another encoding rule. So we have devised a second encoding, which is encoding rule 2, where we have encoding of each of these bit values of the encrypted bit stream, and then we implant the digital signature in the high level synthesis framework. Okay, the chosen layer is register allocation phase of HLS. Now I had already inspired in my previous talks why HLS is so crucial for complex designs such as DSP, because as I'm repeating again, DSP applications are extremely complex and they have like 40 to 50,000 gates. So we can't right away start making the design from RTL or gate level. Okay, so we have to raise the abstraction level, and usually it starts from the algorithmic system or architecture level. So that's how the HLS comes into the picture here. Now once we have this embedding of the digital signature done in the raised allocation phase, then we implant the digital signature and it becomes a digital signature embedded DSP hardware IP. So let us look at the encoding rule for the bit stream generation process. Okay, the rule says if there's an even parity between or this if there's a similar parity between the operation number of the data flow graph and the control step, then the encoded bit is assumed to be a 0. And if there is not a same parity between the operation number and control step, then the encoding bit is 1. In other words, as you could see in this table, the operation number is even and the control step is also even. So in that case, it has a same parity, so the encoded bit becomes 0. Similarly, if the operation number and the control step both are having odd numbers, so they are also having same parity, so again the encoded bit is 0. For rest of the other cases, the encoded bit is 1. So in short, whatever will be the size of the number of operations for a given DSP applications, the bit stream size generated in the first step will be exactly equal to the number of operations. Okay, so how to perform SHA? So first is it generates a decimal digest of a DSP. Okay, the most important properties of SHA is that it provides collision resistance and deterministic properties that ensures that the generated hash digest always is unique for a given IP. So what it means is that the generated hash digest, which carries the vendor secret mark, will always be unique for a given IP core. Okay, so whatever is the IP core, it will always have a unique mapping to that. Post-processing, which is to divide the bitstream digest into m blocks of size n bits each, which I had already spoken about earlier, and each of these n bit block is converted to its respective decimal value. Okay, a little bit brief about what RSA encryption is. I'm sure most of you will already know about it because RSA encryption is quite a strong and powerful tool for security. So in this case, how we use RSA is as follows. So first is this RSA is applied on the hashed digest value of the DSP design. So that's the first novelty that we do here. And so this RSA is applied on decimal by decimal values. So in this case, the input of the RSA is 128 bits. Okay, so for example, the hash 512 generates, or SHA-512 generates 512 bit output. So we will capture 128 bits from there and apply RSA on that. So RSA encryption here in this case is performed using the private key and not the public key. That's very important to note. So what is an RSA? An RSA is an asymmetric key encryption algorithm in which two distinct keys, which is private and public, are involved in the cryptography. It is used to sign the hash digest of the vendor secret mark information to ensure authentication of the genuine owner. So that's the most critical part over here. So as an example, you could see here, so these numbers, which is RSA decimal input, is shown. So these are all 128 bit, and corresponding encrypted decimal output is shown here, and that is of course by using a certain private key, which is again around 128 bit or higher in size, and the corresponding equivalent encrypted binary is also shown on the third column. So there are 4 such decimal inputs to the RSA because we have divided the entire chunk of 512 bits into 4 128 bits. So the output of this RSA module are now fed as an input to the post-processing block 2, okay, which is responsible for converting into binary, and then each of these binary bit streams are then further concatenated to form a single long stream of binary bitstream values. This encrypted hashed bitstream is called as a digital signature. Now once this is generated, now again there's a trick here that the IP vendor now has a choice to truncate the size of the entire bitstream according to his or her will. Okay, so that becomes the strength of the digital signature, or the strength of the constraints that actually would get implanted later into the design. So after this entire stream of ones and zeros are generated, the digital signature can be selected based on the vendor's choice of strength from the given continuous bitstream number. Okay, so for instance, if the vendor selects a digital signature size of 15, then the first 15 bits of the bitstream will be used as a digital signature for implanting. Okay, now let us look into the embedding process of a digital signature. So having created the digital signature, the next step is to embed it in the design. Okay, that's very obvious. So how does it work? How do we implant it? The first is mapping the digital signature into watermarking constraints. Okay, we call it watermarking constraints because eventually once the bitstream gets converted into constraints, it becomes similar to a watermark. However, the pre-processing phase before this was generated is all about digital signature security. Okay, so the rule is as follows: if the bit is 0, then it means that there will be an additional edge that has to be added between prime node pairs in the colored interval graph. So colored interval graph is nothing but a graphical representation of the register allocation phase of high level synthesis. Okay, but if the bit is 1, then the additional edge will be added between the even node pairs of the colored interval graph of the high level synthesis. So we'll see through an example how this zeros and ones affect the internal information or local alteration of the register allocation and the CIG. Okay, so embedding the watermarking constraints. So watermark constraints are embedded in the register allocation step, as I said, during the HLS process, and these hidden constraints act as additional constraints to be imposed besides the regular design constraints of the DSP design. One thing very important, as I had spoken also in my previous talks, that while we implant the hidden constraints into the design, it is imperative that the functionality does not get disturbed and the overhead of it should be as minimal as possible, and the watermarking should not be perceptible to the common human eye. That means it should be invisible by nature. Okay, so before we get into the example, also a little brief about how do we detect a digital signature once it has been implanted. So the first step is called inspection, which is that at the RTL data path of an IP core under test is inspected to collect all the information of storage variables. To do so, the inputs of all muxes associated to each registers are inspected. This inspection provides information of register allocations of all storage variables. So once this inspection is done and all the relevant information of the storage variables from the inputs of muxes are collected, then next is to perform signature verification. Here the objective is to verify the presence of digital signature which was implanted in the collected information of the preceding step. So if this verification process shows that at the inputs of the multiplexers of the data path they contain the same information as the digital signature, then it means that the digital signature is present in the design. Else, if partially it is present and partially it is not, it indicates that some sort of tampering may have happened. Now let us look into a demonstrative example. So the demonstration example that I have picked up for explaining is called 8-point DCT. Okay, discrete cosine transformation. As I said, every camera that we see in our life, whether it's a digital camera, whether it's a smartphone camera, whether it's a tablet or a camcorder and so on, they have underneath JPEG compression decompression IP or IC, underneath which there is a DCT core that actually runs, who is responsible for converting all the spatial domain information of the images in pixels to its respective frequency domain. Okay, so this 2D DCT is useful in JPEG compression process when handling an 8x8 image block pixels at a time. The generic information or equation of an 8-point DCT that computes the first sample, okay, is shown here. So where these values from K1 to K8 are nothing but the DCT coefficients that are available from the DCT matrix, and X0, X1 to Xn, these are the values of the pixels in that 8x8 image block. So using this equation, we have converted that into a data flow graph, as we can see here, and the inputs are that we have a DFG, that also we need a hardware allocation constraint or resource constraint, so we have picked up as 3 multipliers and 1 adder just for the sake of demonstration. So once based on this constraint that we have picked up, the data flow graph of an 8-point DCT is scheduled as shown on the right side, and it takes 8 control steps to complete its final output. As you can see, we have also provided the storage variable assignment from V0 to V22. So there are actually 23 storage variables required to implement this structure. So these red colored lines are actually representing a storage variable, and we also have the node numbers given on the side of each of these operations, which is 1, 2, 3, 4 and so on till 15. So there are like 15 operations here. Now if you look into the table on the left, this is actually just encoding this entire application using encoding rule number 1, which I discussed previously, to generate the respective bit streams. So as I said, if you have like 15 operations, then it will have like 15 bit size of the initial digital signature that will be generated, or encoded bit stream basically. Okay, so it is exactly equal to the number of operations of the application. Now using the encoding rule of same or unsimilar parity, we see that the respective bit numbers are so on. So for example, for operation number 1, since it is also allocated to a odd operation odd control step, therefore the bit generated is 0. Again, if you see the operation number 2, it's an even and the control step is odd, so it does not match, unsimilar parity, so bit number 1 is given. Again, you will have similar parity for 5 3 6 2 8 2 9 5 10 2 13 7, and for the rest it is all 1. So that's how we have the encoding rule used to generate the bit streams. Okay, so let us give a summary of the process now, whatever we have spoken of. So we have a bit stream, okay, which is that bit stream that has been generated by that encoding rule 1 just spoken of in the last slide. And once you have that, then we perform the hashing using SHA-512. The 512-bit hash digest is generated. It is further subdivided into m chunks of n bits, followed by performing RSA encryption of the decimal equivalent of each of these n bit chunks, which is performed using private key value of the IP vendor. This entire process keeps happening until we finish all the 512-bit chunks, and this converted bit stream is then finally concatenated to produce an encrypted data. The final encrypted bit stream is then subsequently truncated based on the size or strength of the digital signature chosen by the IP vendor, and then we have the final digital signature that we get. Okay, so as you can see how the input bit stream gets completely transformed into a digital signature right at the last block in orange. Okay, now once this digital signature bit stream is done, the next step is now to convert it into hidden constraints. Okay, that could be used as a watermark process for implantation. Now this process is using the watermark implanting rules. So as I said earlier or discussed earlier, that whenever we have a bit 1, it represents that an additional edge has to be added between even node pairs. Okay, so that's why for 1 it is v2 v4 because that's the first even node pair, and whenever we have a 0, it implants an additional edge between prime node pairs. Okay, so in this case the first prime number are 2 and 3, so the first 0 indicates v2 v3, second 0 indicates v2 v5, because all of these storage variables are sorted in nature. Okay, so when we want to convert them, we have to make sure that all of these storage variables are sorted first, and then we can employ this encoding rule. So based on each of these numbers from 1 to 10011 and so on till 1, which is the digital signature, the respective corresponding additional edges after decoding is shown on the right side, second column of the table. The graph in this slide on the left shows the final CIG, which is the final colored interval graph after implanting or embedding the digital signature for size s equals to 15. Now let us see how this is built up. So let us look into the pre-embedding table. The pre-embedding table is nothing but it just shows the colored interval graph of the raised allocation table. So the first one, which is B register, which is blue register, that can hold the values of V0, V1, V6, V13, 18, 19, 20, 21, 22. Similarly, the last register, which is BL, which is black, can hold the value of V16. Now if we keep on implanting the values of these digital signatures or this decoded additional edge value, we can see that V2 V4 means that there should be an additional edge between V2 V4, and as we look into the table of pre-embedding, we see V2 and V4 are already allocated to distinct registers R and G. So that means there is no need to change the allocation in order to satisfy this constraint, because whenever we want to add an edge between two node colors, it means that they both cannot be executed through the same register. For example, if there's an edge between V2 V4 for bit number 1, it means there should not be an edge there should not be the same register assignment for V2 and V4. Similarly for the rest. So by default we see we are able to satisfy this constraint of V2 and V4, so we do not need to change anything. Okay, now let's move to the next. We see V2 V3 for bit 0. In this case V2 and V3 both are allocated to same register, which is R. Okay, so that is also visible in the CIG on the left. You can see V2 and V3 are now changed to red and blue. Okay, why? Because we had to change it, because we are imposing a artificial constraint that both of these cannot be allocated through the same register. So the post embedding table below, just below, shows that v3 has now been shifted to blue register, and in that place v1 has now taken over. Okay, because there is no conflict between v1 and v2 in this entire table in the middle. So similarly we keep doing it until we get to the post embedding final table shown on the bottom. One of the most exciting and interesting things here to note is that even after implanting so many constraints, we see that there is absolutely no design or register overhead. Okay, so the pre-embedding process also took, for example, B, R, G, O, Y, C and BL, which is like around 7 registers, and the post embedding process also took 7 registers to implement the structure. Okay, so this shows that digital signature process is almost incurring zero overhead, or is a zero overhead security algorithm. Okay, now let us look into the experimental results a little bit. So we have plotted the design cost for the different DSP applications, where the design cost is a normalized hybrid cost function or fitness function of comprising of latency of the watermark implanted design and area of the watermark implanted design. As you could see, that for each of these applications there is almost no change in the design cost for most of the higher size digital signature values, starting from 30 to 60, 120 and higher. However, there is a slight shift or increment in the cost when we change the signature size from 15 to 30 for most of the cases. Okay, after that it almost remains same, which is of course different in case of JPEG IDCD, which says that the cost absolutely does not change irrespective of increasing the digital signature sizes. So another analysis we have made is using probability of coincidence. This is done to measure the robustness or proof of IP ownership. So lower is the probability of coincidence, more stronger is the design, or more stronger is the proof of ownership in that design. That is how it is defined. So probability of coincidence tells that what is the probability of generating a watermark in a baseline or non-watermarked design. Okay, so this is given by this function 1 minus 1 by c to the power s. S stands for the size or strength of the digital signature. As we could see that with the increase in size of the digital signature from 15 to 240, the value of probability of coincidence indicated by pc keeps on decrementing further for all the DSP applications. So this satisfies our understanding that the value of digital signature, or the strength of the digital signature, should actually lower the value of probability of coincidence. So here we have compared the proposed digital signature security algorithm with another approach 3, which is that uses hardware watermarking. And again we have compared it in terms of the reduction of PC value, which is indicating stronger proof of IP ownership. As you could see that for all sizes of digital signature from 15 to 240, there is a considerable reduction of PC using the proposed digital signature method compared to hardware watermarking 3. Okay, so pretty much done. So the conclusion process now, it's important to understand that this is a new crypto system based digital signature method that is being proposed in the community for the first time, that is able to secure a reusable IP core, especially in the context of DSP hardware IPs. This process comprises of 3 security modules that makes the final watermark constraints robust and secure. And as we had seen, the proposed approach yields stronger protection and security through robust digital signature in terms of reduction of PC on an average of around 24.8% compared to 3, and also significantly lowers the design overhead incurred in terms of the register hardware by around 13.73%. So these are some of the references that I was referring to when we wanted to compare with. Okay, the first one is that approach that has been published in ASIM Transactions in 2005. The third reference is the one which was published in IEEE in 2016, and the fourth one was the one which was published in IEEE Consumer Electronics magazine in 2017. So in compared to all the 3, the digital signature approaches proved to be far superior in terms of higher security and lower design overhead. Okay, so that would be all. Thank you very much for your time, and I hope that this talk was useful to you. Thank you.